I would like to welcome the first presenter, Deјan Popović. He was kind enough to accept my invitation to come and talk. No, I'm going to go. I'm not like politicians, you know. I say what I want to say, and I'm gone for the event. Anyway, that would be nice, actually, if some of these politicians are gone, but I wouldn't talk about that. My presentation was actually, I was aiming to have the first presentation given by my dear friend and our excellent scientist in neurosciences, Professor Kostić, but for reasons that I don't want to go in, we decided to change that and switch to something else. But this is why we have an engineering talk in the neuroscience presentation and the neuroscience presentation given by a non-expert person. But non-experts, they love to talk about things that they don't know because it's so interesting. You don't understand the problem, and then so you can enjoy in talking. So what I will be talking is about the basic ideas that Tomović was introducing. And I will talk exclusively on the walking aspects of that. So I could talk about other aspects of his work, which this is upper extremities, synergies, reaching, hand, and other. But I decided to pick up only one topic and to try to stay focused on walking. So as I said earlier, he was fascinating with movement. He wanted to be perfect in these movements. Since I played tennis with him often, he was always asking me, is my move better? Am I running better? Do I hit better? He was 80 at the time. And upwards, I told him, yes, it's much better, although I have no clue about it. Anyway, so he wanted to see what we can do, and he was fascinated by the idea that the biology and the evolution selected ways and routes that we cannot do in engineering. And he was fascinated by the fact that engineering is trying to use completely different ways and methods that are not found actually in nature. Just a simple example is a wheel. So in nature you have most animals either running, walking, or crawling, or swimming, or flying, but there's no animal which is actually rolling like a wheel. And there is no animal which has wheels, which I don't know why. We're talking to some monkeys, and they refused to have wheels instead of legs. So evolution was there, and with this evolution, I'll start with something that I find extremely interesting. This is something that I picked up, obviously, it has nothing to do with Tomović. This gentleman, Muybridge, who was quite a controversial person, and he was involved into betting with Mr. Stanford, and they bet whose horses are better, and these runs were taking place in California. And in order to actually decide whose horses are running better, they invested a lot of money, and they came with the first photographic system so that they can actually see, because they have two ways of moving in space. This is running and walking. The difference between running and walking is in running, there are phases in your movement where you're flying. And in walking, you always have one contact with the ground. So here you can see galloping of the horse. So in the race, they want to make sure that their horses are running and not galloping. There were hundreds of meters, special ropes, and Muybridge did that. And there's a paper that was published in Nature. And if Muybridge is competing in our competitions today for a scientist, and we look into his age index and the number of citations, you will be fascinating. This paper received 67 citations. Fantastic. So he wouldn't qualify for any of the positions, even not for a PhD student. And then I look into some of other publications that Muybridge has, and his age index is very low, so he really doesn't qualify. But he qualified with some other things very well for that. So Tomović was aware of some of these events, and some of his colleagues were aware of what was happening and how you can do that. And he said, maybe I can use this description of on the ground, not on the ground, as two states of the leg. And I can make a distinction between stiff leg and non-stiff leg as two states. So I have stance phase, I have swing phase, and I can describe events in a series of events which are like that. And this is what I showed you a little just minutes ago. But now I'll explain what this actually does. So the legs are instrumented with sensors. And when the legs are instrumented with sensors, these legs, they feel, they sense is the leg on the ground or it is moving? And these sensors are positioned not only at the bottom, but also on the edges of this disc at the bottom. So the strategy of walking is you need to have 3 legs on the ground, and the surface that is surrounded by these 3 legs needs to include the center of mass, the projection of center mass. If the center of mass, which is called center of pressure, is projected to the triangle, that's a stable position. So the machine will walk, so the leg that is at the longest, widest distance from the center will move in the direction that you want. So you will always have a triangle on the ground and 1 leg moving. So everything is described in states, leg on the ground, leg off the ground. And you saw it here, how this machine works. And this is the movie from 1964. So quite a while. There was a paper that came afterwards, and most of this work was done together with Bob McGee, a good friend who was at the time in California, then moved to Columbus and spent a lot of time, and there were some people from our country, so Vesna Cvetković-Živković, she spent a considerable time working with Bob McGee at Columbus University, and some other also. We had a long collaboration with them. So based on this, we started the project, and Tomović started the project. He came with an idea, and not only with an idea, but he came also with money. And that money came from Veterans Administration, a lot of money, and from National Institute of Health for the work that we were doing in Belgrade at electrical engineering. And what the idea was that we built a leg that will use the principles that I described for a 4-leg machine. And we started the development, and I was involved into the mechanical design. At the time I was teaching mechanics at the university, and I built something that is called cybernetic actuator, and that actuator allows that there is a free state, so the leg can freely move, or with very little friction, that you can control stiffness by controlling 1 motor, and they control flexion extensions. You have a full control, which is alike something that we have with our bile muscles that we're using. So there was one. On the side of that, this has a very interesting design in the sense that you have a non-linear relation because it's a telescopic mechanism, which is extremely low friction that can use for that. So that's one element, that's hardware. But this hardware is of no use if you don't have a software. So the software is an important part, and that's what I'm talking about. And he came with an idea that we will have a controller, which is, this is an image from a paper, journal paper. So it was not drawn by a computer, it was drawn by hand. You can see all the letters, which are not very nice, but that's the way how some of the papers were published. And at the top, there's actually the image or picture of controller. And if you read this controller 8085, then some of you who know about these computers will know that this is the heart of a PC computer. So the only thing which we could use at that time, but there was no microcomputers in that sense, we used actually a chip from the computer that we made an interface that can be used actually to do things. This work was done and greatly contributed with a couple of people from the university, Srbijanka Turajlić and husband Seva Turajlić, Mr. Jauković, who was helping in that, Milenko Cvetinović, who was an expert in electronics, and this gentleman here who was doing his PhD on this, Deјan Popović, who is now in Miami. And what we did is we built actually the leg and the model. These are recordings from 1981 or something like that, 1980. And this was in the Lola Institute at Ada Ciganlija, where we have all these experiments done. And what you can see, there is a complete model of the leg. And what the leg is doing here is we're learning, we're building heuristics that we can bring and transfer to a computer. So this is not writing equations. This is not writing solutions of these equations. It is only on-off based on sensors. So based on detected events on the leg, which are contacts with the ground, force with the grounds, knee joint, angle of the lower leg, angle of the upper leg with the gravity. So this information was sufficient actually to build this device. And that was the reason we built it. And that was the project, which was funded by VA. And what you can see here, there's a gentleman, this is the first time he's actually walking. So we don't know anything about his mechanical requirements. We don't know the length of his leg. Everything is self-adjustable. The leg is self-contained, as you can hear. It has batteries, it has computer, it has sensors. And as you can see here, this gentleman is walking reasonably nice. This work was brought to VA, and a person using this leg was actually playing football in the United States and broke our device and put it in partly because it was not made really to play football. People who want to see that, individuals, you can go to the exhibition, which is in Yakshicheva, and there is actually the original leg that was built, one of those. Now, very fortunately, while I was working on different places, I moved to Canada, and while working in Canada, there was an excellent engineer, and this engineer was not only an excellent engineer, but a good salesperson. He sold that to Arabak, and this is the same leg. So the control that you can see of this GNU mix, these recordings are for 2018. So as you can see, there is a full adaptation of the leg, and it has a different actuator, which was built by Arabak, but it has the same control. So there's a rule-based control, finite state control, where you do not actually calculate what are the power that you want to. And I think that this is tremendous how he's walking. I know perfectly well that I wouldn't be able to walk like this gentleman here. So the thing that I need to do is to do an amputation, and maybe then I can do better, which I don't plan to do. So anyway, I think that's a fascinating example on how far it can go. And that's a fascinating example how some ideas of transmitting what we can learn from nature can be implemented in something that is made by a human. So in this control, I was talking here about the leg. Building artificial leg is much easier than assisting a person with paralysis to stand and walk. Because in artificial leg, you control everything. It's your mechanical design. There's space to put sensors, space to put actuators, everything is there. So you actually can do very well. But when you're talking about a human, you cannot really take out all the muscles and bones and put your stuff in. And you have to make a system which will work in parallel to what the biological control does. So what you can do is you can actually analyze in detail which muscles are active and can represent, and what you can see here, changing colors. So these colors are changing, showing muscle active, muscle not active, muscle active, muscle not active. And you can link this to the locomotion cycle. So you know in which phases of the gait cycle, which muscle is active. Of course, you cannot activate all the muscles, and you cannot do the same as nature is doing, but you can do a lot. So if you do that, you can actually see at the muscles, and you look at the right side, and you can make something which is called a lookup table, which is if-then. So if a specific event is there, then a specific activity needs to be done. This is what is called rule-based, if, then, else, if, then, else. And Tomovich made the control so that you have a sequence of reflexes that will actually make the movement happen. So we did a very nice simulation of that. And here you see the rule-based control applied to a model. The model looks like a cat, but it's actually a biped or a human walking with the walker, because this front part is like a walker. And it's a 3D, and what we could do is we can actually simulate and look very well what will happen if the conditions are changing. So if this is walking, this was on the moon, so you decrease the gravity. Here you increase the gravity force, and if you increase the gravity, you see a completely different pattern, but it works, and if the force is too big, the system cannot operate anymore. So you can actually check and see very nice how it works. We did and went a step further, and we actually wanted to see how it works in real life if we are stimulating and activating muscle, and that's the work that I was doing in Canada with Dick Stein and some excellent people in Edmonton. And what we did, we instrumented animals with electrodes that were on nerves and muscles, and we were looking. So what you can see, these are recordings from nerves and muscles that you don't understand at all, and that was not my intention that you understand, but just to show that it's doable. And then if you do some processing and you make envelopes, you have these signals for the walking cycle. But what's the means of that? So if you have these, then you can use machine learning in this specific case. This was calculating the maximum probability. And if you calculate it, you find the threshold. You can actually find the rules. And these rules are, if you look at the left image, you see 4 rules. And these 4 rules is through the walking events, based on sensors information, you will actually do something. And this is how it works. These are actual recordings from a cat. These are experiments that were going for years in the 90s. So this is a partly paralyzed cat. So the leg is paralyzed. So we're recording nerve activity, and based on the recorded nerve activity, we're stimulating muscles. And when we stimulate muscles, the cat is walking on a treadmill. We change the speed of a treadmill, we change the slope of a treadmill, and the cat automatically adapts. And it's completely, again, rule-based, finite state controls, If the sensor signals in this are nerve recordings, then specific muscle activity needs to be induced. Very complicated experiments, but the good thing with that is that you can actually transfer that to something where it has meaning, because there's no reason in trying to repair a cat in that condition, but scalping a person is good. So we try to do that, but obviously you cannot do it in humans like you would do in experimental animals. You have to do it in a less invasive way, and in a less invasive way you don't have the information that is that precise, and you don't know the characteristics of the system, but you can do some coding, and if you do that and you use machine learning in that, and quite several students that were graduated with me, they actually did a fantastic work in trying to find out what sensors information is required and which muscles you need to activate. So what you see here is based on this machine learning is, on the right graph, you see these squares, rectangles, and you see underneath the muscle activity. So machine learning is coming with squares, and the real activity is what was recorded in an animal that walks. So when you use this and you implement that, then you can actually assist the person who is paralyzed. So this is 6-channel stimulation of a person who is paralyzed from his back. This is the patient who has an injury at the T6 level. He has ankle-foot orthosis. He's using the walker for support, and he can walk like that. We had 12 patients in the study. We can make them walk fast. We can make them fall. So everything is still a state machine, not finite state rules that may work in that operation. That in humans doesn't work very well, because you have this jerky movement. Turning on the muscle, turning off the muscle is not really the way to do it. So at the actuator level, you need actually to do a little better than that. And to do that is you offline do the simulation, and you find and define profiles. And when you're defining these profiles, you make a model. You use a very complex model, which is a component. You apply this model in something which is MATLAB or something like that. And this is the work which was done by one of my very good friends and students, rođeњa, who is now in Denmark. This was part of his PhD, this MATLAB program, not the rest of that. And then you select a gait pattern that you would like to do, and what it will give you, is this here. So for the trajectory that you see there, you have now profiles of stimulation which are not rectangular anymore. So it's a modulated activity that you want to introduce with this. Obviously, this is not exactly how that will happen in nature, because you cannot do it with electrical stimulation, but it's doable to a specific point. Going further on, we implemented this, a combination of that, in a slightly different way from what I presented now. There was a newer development. And here you see one of the 12 children that will participate in the program in Canada, who is using now a combination of external stimulation, electrical stimulation of muscles, and using orthotics, so exoskeleton. And this exoskeleton is a modular exoskeleton that we built, which has a reciprocating gait mechanism, which is at hips. It has ankle-foot orthosis, and this young gentleman was going into school like for 2 years with that, and use it throughout the day. Unfortunately, the funding of some projects stops, and we got sued at the end by the family because we stopped the program. But that's a problem with development, because this is not the part of the healthcare system, and if it's not part of the healthcare system when the project stops, there's not very much you can actually do with that. So based on all of that, we published a book where most of these things are described in reasonable detail, which is, through my eyes, very important. And I fitted my talk in the time. So what I wanted to say is one example of Tomović's idea and transfer of technology, and I hope that I brought part of that idea to you. Thanks. Question?